Hello and welcome to another wonderful lecture on spectroscopy. So today we are going to be looking at vibrational spectroscopy. So this is essentially going to be spending some time with our old friend of infrared spectroscopy with a little bit of touch of focusing in on vibrational energies. So one of the first things I want to focus in on is going to be this vibrational energy perspective, because when I'm looking at vibrational spectra, what I'm really looking at is how is the movement of atoms in a potential well. So if I have two atoms, they've got a distance of x away from each other, focused around some equilibrium uh, bond length. And what I'm really looking at is going to be the fact that molecules tend not to stay still. So I'm going to have one of the atoms moving back and forth in the effective field of the other. And so what we're really going to be needing to focus in on is, like we developed earlier, we need to figure out the general shape of the potential well. So we need to find a good expression that defines the potential well in which this atom is moving. So there's going to be an almost infinitely high barrier as the two atoms get too close to each other, and there's going to be some tail off, a long tail off on the other end, where eventually we asymptotically approach dissociation, where if I get far enough out, the atom is barely bound and will just freely dissociate. Now, the problem is that it turns out that uh, this sort of tailed potential well is actually fairly hard to model because, well, who doesn't love an infinitely tailed species? It's hard to describe this one well. So our go-to approach is going to be to use a Taylor series. So we have a zeroth order term that depends upon the displacement x. Then we'll have a term that depends upon the square of the displacement, the cube, the quadrat. And again, we're trying to expand across about some central point 0. So again, we're 0 displacement, so 0x is going to be centered around the equilibrium bond length. And I'm going to try and fit this Taylor series to this full this full energy curve. So the full potential well curve. Now, again, problem we end up running into at this point is going to be, like most Taylor series, I don't want to expand infinitely far. So what we'll do is what we often do, and we'll ignore any cubic term or greater. So anything that's the cubic term or more, we're just going to drop off and focus in on these three expressions. Now, by convention, we often don't care what the actual energy is. We care much more about energy differences. So we're going to set our 0 displacement energy to 0. In truth, we'll come back later and we'll correct this with the electronic energy term. But in terms of just vibrational energy, this guy is 0. Now, since I'm also expanding about this curve, we may notice that because it's an equilibrium, it turns out that, well, the first derivative is going to be 0 because it's a minimum. So by definition, these two expressions drop down to 0. So we're going to be able to set these two expressions to 0 and ignore any higher order terms, at which point my full potential expression gets rather straightforward. It's going to depend upon 1/2 the second derivative of the potential times the displacement squared. Now, at this point, our major trick is going to be focusing in on what's this second derivative value. So this is just going to be an arbitrary constant. Now, how we determine this constant is always going to be the real rub. But it turns out that this equational form turns out exactly like something we've done before. If we're just looking at this second term expansion of a Taylor series, this is actually how we get to the harmonic oscillator, which we previously built up. And I simply replace my second derivative term with a force constant. So again, this force constant is going to, in large part, represent the stiffness or strength of the bond. And again, can also be described as the width of the well. The smaller, the smaller the Kf value, the more narrow the well, the stiffer the bond. Now we can go ahead and uh, apply the Schrodinger equation like we did previously, and what we'll find is that out will pop some discrete eigenvalue energies of this potential term. Of course, once we combine it with the kinetic energy term. So if you want to go ahead and verify of how we get these as energy eigenvalues, I encourage you to go back to the end of chapter 7. But once I have these energy eigenvalues, this is going to give me all of my various energy levels. Now, we're going to be able to diagnose this expression down to several key terms. First is V, which is going to be our energy quantum, or our key vibrational quantum number. This value will go anywhere from 0 to some V max. And it is worth noting that the zero state does not give us a zero in energy. So this also reflects the idea that molecules do not stop moving. There will always be some residue energy value of 1/2 h bar omega, which we define as the ground state energy. So this is actually a key feature when we're trying to correct the electronic energies we spent so much time building up, that we often need to know these vibrational energy numbers. However, what's our omega in this case? So in this case, omega is our vibrational frequency, which can be determined using the ratio of the force constant and the effective mass. So again, in this case, the effective mass is going to focus in on the effective mass of the two vibrating atoms as we develop this system for diatomics. And we'll work on polyatomics a little bit later. So again, our vibrational frequency is going to be the square root of the force constant divided by the effective mass. And so the smaller, the tighter, the stiffer the bond, and the lighter the molecule, the faster the atoms are going to have to vibrate back and forth to stay at equilibrium. Heavy molecules and weak bonds lead to slower vibrations. Now, what us being us, we're going to be trying to express this not in terms of energies in joules, but again, in the energy in terms of wave numbers. And so this is given as the vibrational term. And again, what we did is we collapsed all of our constants down to a vibrational constant, which is going to be, again, based on our based on the square root of the ratio of the stiffness of the bond over the effective mass. And then again, we have to build in some unit conversion. Now, instead of using Planck's constant, we're using 1/2 pi speed of light. So this will give us the energy of each of our energy levels. But what we're going to be focusing a little bit more on is peak location. So this is going to be the energy difference between levels. And for that, we need to make use of selection rules. So it turns out we actually built up selection rules for a harmonic oscillator previously, and it turns out that when you apply your selection rules, that vibrational states are only allowed to increase or decrease by 1. So if I'm putting in energy, we'd expect the energy, the vibrational quantum number to go up by 1. So increase in vibrational states is an increase in energy. And if we release a photon, we typically expect it to decrease by 1. And again, there are some notable exceptions when we start coupling it to things like electronic energy excitations. But for our purposes, what we're able to then do is derive a vibrational energy change or peak location in wave numbers simply by using the difference in between uh, our ground state of quantum vibrational quantum state of V and the excited state or final state of V plus 1. So if I'm excited from a ground state of V to a state of V plus 1, I can then take the difference of these two, and it turns out that the V plus 1 terms end up canceling out, and all I'm left with is a single vibrational constant. So, congratulations. This is actually fairly unique in that, unlike the rotational states where the energy separation changed based on the identity of the ground state, for vibrational cases, it turns out that as long as we obey the harmonic oscillator, all states are separated by the same energy. And so, functionally, this is actually quite nice as it will give us a single peak to measure. Now, it is worth noting that we are assuming the harmonic oscillator, uh, which tends to work at best at low values of V. Because again, we built this by doing a Taylor expansion from the equilibrium value, and we only tend to stay fairly near the equilibrium bond distance for fairly low vibrational quantum numbers. However, this actually turns out to hold pretty well for most room temperature molecules, because it turns out that the energy separation for most molecules is fairly significant. So we only really expect the V plus 1 state to be occupied for frequencies less than about 2 or 300 inverse centimeters. And if you remember your IR spectra, or if you go ahead and look at some of your vibrations from lab, you're going to tend to notice that most vibration states we care about have frequencies much greater than 2 or 300 inverse centimeters. So turns out that this is actually a fairly good approximation. However, sometimes we do care a little bit more about those low energy frequencies, or we care about high temperature systems. And as temperature goes up, I tend to occupy higher higher quantum states. So I'm going to tend to occupy the V equals 2, 3, 4, or 5. So if I'm wanting to describe the potential energy of a system further from equilibrium, so if I decide that the harmonic oscillator is too much of a severe approximation, which honestly, occasionally it is, we need to often fall back on our old friend, the Morse potential. And you may have seen this in lab or heard me make use of it. And so the idea of the Morse potential is at this point, we were able to obtain more accurate potential energy surfaces or wells for molecules and fit a much better equation to it. And it turns out that the Morse potential describes most vibrational quantum wells or energy wells fairly well. And so what we can end up doing is looking at the Morse potential, we can divide it into two major parts. So we have a damped and offset exponential expression, which essentially is going to give me the general shape of a a rapid increase of the potential towards infinity at values near zero, and values that damp towards zero at fairly large displacement. So this gives me the shape pretty well. And this first correction term on the outside essentially gives me the depth. So it will scale this shape either up or down. Now let's try and diagnose these expressions a little bit more. So let's focus in on the general shape with this exponential term. So we have a constant a, which essentially is a shorthand because I don't want to write out this full expression. And so our a term essentially is going to represent our effective mass times our vibrational frequency over, again, this dE value, which shows up again. But it's worth noting that you can actually combine our effective mass times the square of the vibrational frequency, and more or less what you get back at that point is the force constant. So what this is going to be telling me a lot is about the stiffness of the system. So if my A expression is fairly large, I'm going to be seeing a narrower well here. And if A is smaller, I'm going to tend to see a much wider well. Now, the other feature that we need to focus in on, because it shows up twice, is this HC uh, uh, DE expression. So again, we can see by the tilde that DE is going to be expressed in terms of wave numbers. So HC is just simply a conversion from wave numbers to energy. And so really what this DE expression is going to give me is the depth of the electronic well. So what's the difference in between the energy of the system as low as it can get versus the energy of the system when it's completely disassociated? So again, the depth of the well. At infinite separation, what's the energy of my two atoms? So what's the energy to break the bond, to get out of my electronic well? So if, for example, I was going to find the electronic energy via some molecular orbital calculation, and I wanted to figure out the energy to separate the system, so I did an electronic calculation, this is the number we'd really get. This is the electronic dissociation energy. And so again, that's one of the reasons it shows up as this prefactor, is it scales my system down to make sure that my well is as deep as the electronic system. So again, we often need to fit this with some other model. But there's also one other thing that should be noted, as I called this relatively the disassociation energy. But we run into a slight problem, and that's the fact that atoms never stop moving. So I will never find my system at the bottom of the well. And we found this earlier with this ground state expression, because my V value will always have a value of 0 or greater. So at 0, I'm still some energy above that minimum well depth. And so if I wanted to actually go out and measure the bond dissociation energy, the number I'm actually going to get is going to be this D naught. And this is really just my bond dissociation energy in wave numbers. And these two numbers, the electronic versus the 0-point energy, are going to differ by the energy of my original ground state. So again, we already know how to obtain this value using the harmonic oscillator approximation. This is going to have an energy of 1/2 my vibrational constant. But we'd also like to be able to get my energy levels out from the Morris potential. So unfortunately, in order to do this, we're going to need to take this expression and put it in our Schrodinger equation and solve. And it turns out that is very ugly, so I won't make you do it. And what we end up getting out is going to be an energy expression, which is going to, from first order, pretty much be my harmonic oscillator energy. But what we end up spotting is that there's now a new correction value. So we have a correction value that's, again, going to be based on the vibrational quantum number, the vibrational constant, and some new weird constant called xe. This xe is essentially is the anharmonicity constant. And what it's going to really reflect is going to be the fact that as my vibrational states get higher in energy, I'm also going to expect the energies to get closer and closer together. So that's also the reason why here we have a factor of the quantum number plus 1/2, and here we scale that as squared. So at large quantum numbers or high vibrational states, it turns out that my anharmonicity factor is going to start dominating and bringing my vibrational states much closer together in energy. With this term dominating for high vibrational states. Now let's try and actually diagnose what this antiharmonicity constant is. So it turns out that it's related to really the ratio of the stiffness of the bond and the depth of the well. So if I have a fairly stiff bond, what I'm going to end up seeing is I'm going to get a fairly large antiharmonicity constant, and I'm going to drive my energy levels fairly close together. And we can think about that as if I bring my well a little bit tighter, then congratulations, what I did is I more or less forced the level of each of these states up. So again, if we tend to think of, like we have previously, my vibrational states as, or my potential surface as a lake. I have a given water level, and if I start tightening if I reduce the surface area of the lake, that means I'm going to increase the water level. And that's really what we're seeing here, is that's going to drive my vibrational states closer and closer together. Otherwise, I'm just going to flow out of the system. Similarly, the deeper the well, the smaller the anharmonicity constant, and the less it's going to end up influencing the system. Because as the well gets deeper and deeper, the harder it is to break the bond. It turns out I can actually stack in more vibrational states before I threaten to spill out and hit this nice long exponential decay. However, it is worth noting that in practice, we often don't use this energy expression, and occasionally we end up introducing a third order term. So again, this is our first order harmonic oscillator, second order Morse potential, and then we can end up introducing third order expressions, which tend to follow very similar patterns and increase the resolution of our data a little bit, but tend not to be often worth the increased time it takes to calculate the system, unless you're after very high resolution data. However, again, we are often less interested in the energy levels and often more interested in the excitation energies. So we can look at the excitation energies or the peak locations by simply taking the difference in between our initial state and the state that is one vibrational state higher. So again, based on our selection rules, my V will ever only increase by 1. So I can go ahead and put in these two expressions. For now, I'm going to ignore the third order term. And if I'm just using a Morse potential, what we end up having is a peaks that will be centered on we'll find peaks that are going to be centered on the classic harmonic oscillator solution. And then I'm going to find several peaks that are slightly lower in energy. They'll find, then my peak will be slightly lower in energy as the V increases. So if I was going to say take a spectra of a system that's spread over several different vibrational states, if I will have a single peak for V equals 0 that's slightly lower than I would expect it based on harmonic oscillator. And then I'll have a second and third peak that are going to be slightly lower in amplitude because I will have less species in those excited states, but are increasingly downshifted. So when we're looking at trying to read a vibrational spectrum, and I'm interested in that ground state system, that 0-point system, so that V equals 0 case, I'm going to focus in on that high intensity first peak for most of my analysis. However, one of the other things you should watch out for is that when we try and apply our selection rules for the harmonic oscillator, the only excitations that are allowed is from V to V plus 1. It turns out that once you account for the asymmetry provided by the Morse potential, a lot of these forbidden transitions tend to be allowed. And when we have these classically forbidden transitions, we tend to call them overtones. So for example, my first overtone is going to be the 0 to 2 transition. My second overtone is going to be the 0 to 3. My third is going to be the 0 to 4. Now, one of the other questions we want to ask is, where would I expect to spot these these peaks on a traditional spectra? Well, you can actually redo these numbers, and you tend to find, especially if I was only counting the classic harmonic oscillator correction, I'd expect my peak to be located about twice my vibrational constant. So 2 times further downfield. So, for example, if I'm looking at a classic CH stretch at 3000 wave numbers, my first overtone would be located closer to 6000, which it turns out you actually won't spot with most infrared spectrometers. In addition to being much outside of the traditional resolution, we additionally have to worry about the fact that these are still weakly forbidden. It's hard to get my initial and final states to line up with that photon. So these will also be at much lower amplitude. So if you're looking for the overtones experimentally, you often need to have specially designed equipment or at the very least procedures. So this brings us to the end of pure vibrational spectroscopy. Next time, we're going to be trying to look at how vibrational and rotational spectroscopy may end up being related. Till then, take care and stay healthy.